Let's talk about vertex form of a quadratic. Vertex form is a new form to write a quadratic in, y equals a times x minus h squared plus k, that gives us a different set of information than standard form did. You remember standard form was y equals ax squared plus bx plus c. And the only thing it really told us right off the bat was the y-intercept is at c, and if the graph is pointing up or down with the a value. We could find the AOS by doing negative b over 2a, and then find that, plug that in to find the vertex, and there's stuff we could get from it. But vertex form gives us a kind of different set of information to work with. With vertex form, believe it or not, it gives us the vertex at the point h comma k. So say I had like y equals 3 times x minus 4 squared plus 5. The vertex here would be at the point 4, 5, not negative 4, 5. You're going to see that and think, oh, negative 4, 5. But because of this minus here inside that parenthesis, you want the opposite of this value for the x-coordinate of the vertex. The outside one, the y value doesn't change. Just take it as it is. But for the x-coordinate, you take the opposite. And if you're wondering why that is, you know, we could discuss that at some point. The short answer is it's whatever makes this equal 0. And so to make that equal 0, the h value has to be positive 5. So when you plug in a negative 5, you get even that's not helpful enough. But you take the opposite. Just take my word for it. And the AOS is at the line x equals h. So that would be here. The AOS is the line x equals positive 4, not negative 4, because the h value is 4. If a is positive, the graph goes up. If a is negative, the graph goes down. That stuff hasn't changed. And I'm going to talk about one of my favorite tricks when it comes to graphing quadratics. I call it the first step. You can use a to take your first step from the vertex. Let me show you what I mean. I'm going to just make up some quadratic here. Before I make up some quadratic, I'm going to graph the parent function. The parent function is y equals x squared. Y equals x squared is the parent function of a graph, meaning it's the basic, plain, boring, stripped-down version where nothing special has happened to the quadratic. It hasn't been dilated, it hasn't been reflected, it hasn't been slid around at all, and sliding around is called translated. That was a nice curve. Let's see if I can do as well on the left side. Yeah, those are some pretty parabolas I'm doing there. We should all applaud me next time we see me, which, you know, I'm seeing me now, kind of. There is the parent function y equals x squared. And it actually follows this really predictable, useful pattern. From the vertex, if I go one step to the right, it goes up 1. If I go another step to the right, it goes up 3. And if I go another step to the right, it goes up 5. And the next step to the right will be up 7, and the next step will be up 9, and it keeps increasing by 2 more each time. So now this isn't a slope. We're used to talking about slopes where you have a constant rate of change. Up 1, right 1, up 1, right 1, up 1, right 1. The rate of change is constant. With a quadratic, the rate of change is not constant, but the rate of change is changing in a constant way. And that's a little bit confusing, so let me just write down the integers here, make a table of integers. I'll go from 0 to 7. These are technically whole numbers because they didn't go negative, but whatever, they're still integers. And if I square 0, I get 0, and I square 1 for 2, and square 2 for 4, not 2. 1, 4, 9, 16, 25, 36. I skipped 6 because I'm really good at counting. Believe it or not, counting is one of my strengths, so don't hold that against me. Okay, what I have on the right side here is all the perfect squares. 0 squared, 1 squared, 2 squared, 3 squared. And we notice that they increase by a different amount each time. Up 1, then up 3, then up 5. But now we can see there's a pattern to how they increase. They're increasing by 2 more each time. And that pattern of how they increase is really useful when you try to make a graph. What I just wrote down here in green, these are called the first differences. And you might remember from Algebra 1, if the first differences are constant, you have a linear relationship. But if the second differences are constant, from 1 to 3 we go up 2, and from 3 to 5 we go up 2, and from 5 to 7 we go up 2. These are all going to be up 2, up 2, up 2. If the second set of differences are constant, you have a quadratic. If the third differences were constant, it'd be cubic. If the fourth differences were constant, it'd be quartic, a fourth degree function. But the second differences with quadratics are the same, which gives us a very handy pattern that we can follow. From the vertex, go up 1, then up 3, then up 5, then up 7, then up 9, wherever the vertex is. So let me just do a quick example for you. Here I'm going to graph y equals 3, not 3, sorry, I'm going to keep the a value at 1. Y equals x minus 2 squared plus 4. Well, what this does is it gives me a vertex at the point 2, 4, and an AOS at x equals 2. So I'm going to, just like here, I'm going to call this the point 2, 4. Because I know this graph is going up, the a value is 1, so the graph is pointing up, so I'm giving myself space to move upwards. And then I'm going to draw a couple axes on here so I have a frame to work with. If my x value is 2, then the y-axis is here. If my y value is 4, then my x-axis is actually kind of down here, but we'll live with that. That's okay. This is going to go from this point 2, 4, up 1, right 1, up 3, right 1, up 5, right 1, and then it would go up 7, right 1, and then up 9, right 1, but I can't squeeze all that on there, so I graph another perfect parabola. I kind of missed a little bit down here. You try and do better. You can't. And it does the same on the left side. Up, left 1, up 1, left 1, up 3, left 1, up 5, and this is the pattern that I use to make my parabolas. I just take one step to the right, up 1, right 1, and then up 3, up 5, up 7. Now this pattern will change if you have an a value that isn't 1. So it usually goes, from the vertex, up 1, up 3, up 5, up 7. But now we can always multiply that by the a value. So it's actually going to go down 2, down 6, down 10, down 14. It's going to go down 2, down 6, down 10, down 14 from the vertex. So that pattern that I have of 1, 3, 5, 7, which I don't think is that hard to remember, and even just 1, 3, 5 is probably enough. You rarely have enough space to move that fourth spot. That pattern, 1, 3, 5, 7, just gets multiplied by the a value. So vertex is at -5, 4. And since this graph is going down, I know it's going down because the a value is negative, I'm going to put this point like here and give myself a lot of space to go down. So I'll draw an x-axis around that. 1, 2, 3, 4. Here's the y-axis. Sorry, if that's at -5, the x value, y-axis, this should be here. Now it has an x value of -4, an x value of -5, excuse me, and I want a y value of 4. So that's here. I really recommend you do this when you're graphing. First put down the vertex at the top or bottom, depending if you're going up or down, and then go from there. Pick an axis from there. So, from this point, this is my first step. This is why I call it the first step, because this value here will always be one step to the right from the vertex. Go down 2, right 1, down 2, left 1. Okay, so you can actually make those 3 points right away from vertex form. Then, you go down 6. 1, 2, 3, 4, 5, 6, right 1, and left 1. And I don't have room to go down 10, I'm out of space, but here is my pretty parabola. So see if you can think through how this next graph is going to work before I start actually doing it, this one over here. The vertex is at 2, 0, and the graph is pointing upwards. So I'll put 2, 0 like here. The a value is 3. Is that correct? Yes, a value is 3. So from 2, 0, the first step to the right is up 3, and first step to the left is up 3. And now say you can't remember the pattern from there. I mean, the pattern goes up 1, up 3, up 5, but then times the a value. So the next step is technically going to be up 9. And going up 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. I have just enough space for that. It's there, great. But if you're stuck with that, you can always still just make a table and plug in points for x and get out stuff for f of x, which means y. So I know that the vertex is at 2, 0, because there's a plus 0 here on the end if you don't think of it that way. The a value is 3, the h value is 2, the k value is 0. And then put that in the middle and plug in points above it and points below it. And that's great. So if you can't remember this little pattern, just graph like you've always graphed by plugging in points. I just think the shortcuts are nice. This had a root at the point 2 and a y-intercept at 12. So this is like 1/2 x plus 0 squared plus 2. Think of it that way. It's still in vertex form, even though it's missing that parenthesis that we are kind of getting used to seeing. So just add in a 0. You can always add a 0 whenever you want. I added one here, and I can add one here. So this is a vertex at 0, 2. It's again pointing down, so I'm going to put 0, 2 here. My first step to the right and to the left are both going down a half. So this is not an actual slope. I can't go down 1, right 2. It's not a slope. It's a 1 step to the right and 1 step to the left. The pattern went 1, 3, 5, 7. So if I do those times a half, if I do all those times a half, I'll get 0.5, 1.5, 2.5, and 3.5. So now I can go, I went down a half, now I'll go down 1.5, now I'll go down 2.5, now I'll go down 3.5. And I could go down 4.5 for the next and 5.5 for the next. Let's do it. I can fit it on. 1, 2, 3, 4.5. So the next point would be here. I go in the other direction, so I've gone down a half, down 1.5, down 2.5, down 3.5, down 4.5. Looking good. With all these points, which I just made really, really quickly, and not by plugging stuff in, just by taking the numbers 1, 3, 5, 7, all the first odd numbers, and multiplying by a half. And I made what started as a really good parabola and ended kind of poorly. That one also. If I was going to turn this in, I would fix these, but you don't want to watch me try and make parabolas over and over and over. So I'll just put on an axis and call this good. 0, 2 would be here. Good stuff. Now, one of the useful things about vertex form is you can take a vertex, or a graph that has a vertex in it, and write the equation of it. This has a vertex at the point 1, 3. So I would write y equals a times x minus 1 squared. People forget the square all the time. Don't forget the square. It's a quadratic. X minus 1 squared plus 3. Now, I just have to find the a value. And it turns out finding the a value is really simple if you know this trick. From here, 1 step to the right, 2 steps down, the a value is -2. Just check what your first step is from the vertex. It only works from the vertex. Check your first step and go from there. And then to convert this into standard form, I need to just do some foiling, some distribution. I'm going to take my vertex form, and I'm going to square this. I have to do the squaring before I try and distribute this -2. Because of order of operations, I have to do exponents before I multiply. So don't try to multiply the -2 first and then square things. First of all, that's kind of a pain. It actually just makes things harder. If you want to write it out like this, which I do typically anyways, this is really what we have. Now, I'm going to do this first. You could do -2 times x minus 1 first if you wanted to, but I don't want to. I want to do this first. There's actually a shortcut for this that we learned in Algebra 1, so I'm going to do it kind of quickly. It's -2x squared. I'm distributing now, plus 4x minus 2 plus 3. I distributed this -2, which gives me -2x squared plus 2x. Sorry, still minus 2x plus 1. -2x squared plus 4x minus 1. This should have a y-intercept at +1, and if my math is correct, it does. That's a good way to check to see if you've done your converting correctly. Okay, we were able to find this in vertex form pretty quickly because A, we knew the vertex, which made this pretty simple, but B, we could find the a value. We could find this -2 because we could clearly see the change from the first point to the second point, from the vertex to 1 point away from the vertex. But if you don't know the a value, like here, this is going right 1, but up some unknown amount. You know, I can't say it's going right 3, up 3, because that's not the first step from the vertex. It only works for 1 point to the right, like literally 1 unit. So if your grid isn't counting by ones, it's also no good. But if you can't tell what it is or you forget this little trick, well, we still have other options. For example, this vertex is the point -4, -2, which means I can write y equals a x plus 4 squared minus 2, because my a value is 4, my h value is -2 from that vertex. Then I pick some other clear, well-defined point on my graph. Like this is the point -7, 1. Well, that's x and y. X is -7, y is 1. I can go to this equation and plug those numbers in for x and y. 1 equals a times -7 plus 4 squared minus 2. Now I can solve this for a. 1 equals a times -3 squared minus 2. -3 squared is positive 9. So 1 equals 9a minus 2. I'm going to add that 2 to both sides to get the a by itself. 3 equals 9a. Divide both sides by 9. 1/3 equals a. So this is the equation y equals 1/3 x plus 4 squared minus 2. That's the equation in vertex form. To check this, there's a couple things I could do. One is just pick some other point and plug it in. Like here's the point 1, 1. If I plug a 1 in for x, I should get out, sorry, that's -1, 1. If I plug a -1 in for x, I should get out 1 for y. -1 plus 4 is -3, is positive 3 squared is 9, times 1/3 is 3, minus 2 is 1, I got out a 1. I plugged in a -1, I got out a 1. That's a very good sign we did it correctly. What we're doing now is we're doing transformations. We've talked about transformations before in this class. We did absolute value transformations, a times the absolute value of x minus h plus k. Where h and k slid things left and right, a dilated things, and if a was negative, it reflected things. Well, here's our parent function. And then every other parabola is in some way a manipulation of this parent function. So, like, this parabola here, this equation, is going to manipulate this one by doubling all the y values, sliding everything to the right one, and sliding all the points down 5. So like all these y values that were like this, we used to have 0, 0, and 1, 1. Well, 1, 1 will become 1, 2. And 2, 4 will become 2, 8. 0, 0 doesn't change because 0 times 0 is 0. But the y values now go up twice as fast. Then the graph gets moved right 1 and up 5. So this goes right 1, down 5. 1, 2, 3, 4, 5. Right there. And this graph will basically just match this graph. Yeah, my curve wasn't perfect because I drew it by hand, but everything was slid right 1, down 5. These are transformations. There's 4 possible transformations we do in this class. Eventually we'll tack on a 5th. When we get to trig, we'll do horizontal dilations, but right now we're just doing a vertical dilation. So if the transformations can be reflected, this one wasn't reflected over the x-axis, it can be dilated by a factor of 2. I should technically say vertically dilated, but I don't want to worry about that right now. Then it was translated, which means slid around. Translated is different from transformed. Translated right 1 unit and up 5 units. Those are our transformations, which are shown with a, h, and k. If the a value is positive or negative, the graph will be reflected if it's negative. That shows reflection. The reflection happens if it's a negative. The a value does your dilation. The h value translates things left to right. The k value translates your parent function up and down. So if I was going to list all the transformations in this one, this covers everything. First it was reflected over the x-axis. Next it was dilated by a factor of 1/4. You need to list these in order from left to right as you read them. It makes a difference. If you translate then reflect over the x-axis, everything changes. Then it's translated right 2 up 7. Those are just units, whole number units on our grid. Those are the 4 possible transformations. I only list 3 because there's 2 different types of translations, left, right, and up, down. Let me show this before I talk about this. Let's talk about this on Desmos. And you can type any equation into Desmos and keep your y's and your x's, y's, and x's, but you can take letters and just type in letters. So here's a times x minus h, close that parenthesis, squared, I'm going to type the square button here, plus k. And it says when I add sliders, yeah, add all those sliders. Watch how right now the hk is 1 and 1. So there's the vertex at 1, 1. Let's move that to 0, 0. Let's just type it at 0. 0, 0. As a gets bigger, the graph gets more narrow. As a gets less than 1 but positive, which happens here, it's really, really getting wide fast. And for a split second, it's flat. If the a value is 0, it's like all this is gone, and it's just the line y equals k, because the a value is 0. But if the a value is anything non-zero, there's your curve. Now it goes negative, and it reflects, and gets steeper and steeper and steeper and steeper. And then you can see how the h value moves things left to right, k value moves things up and down. Really worth playing with, and a really great way to graph.